Okay, on the sheet that was significant figures and propagation of errors, there was a question involving a coin of diamonds. This also related to the question that was about the gold nanoparticle. So the method that we're going to use would be exactly the same for the two. So the question in the worksheet asked, determine the number of carbon atoms and error of a circular coin of diamond prepared by vapour deposition that has a radius of 4.005 with an error of 8 centimetres and a thickness of 5.06 with an error of 4 millimetres. And I give you the density of diamond and the relative atomic mass of carbon. So the volume of the coin of diamond is given to us. V is equal to the area of the coin multiplied by the height, so pi r squared d, or pi r squared h, depending on what you want to do. And so the volume is equal to pi multiplied by, what I need to do is I'm just going to make this 4.005, that's centimetres, but I'm going to have my depth in centimetres as well. So it was 5.06 millimetres, I'm going to change that to be 0.506 centimetres. So here, my volume of this coin is 6.37 centimetres cubed. So a pretty big lump of diamond. So the uncertainty in my volume divided by my volume is equal to my uncertainty of my radius divided by my radius plus the uncertainty of my radius divided by my radius plus the uncertainty of my depth of the coin divided by my depth of the coin. The reason I've got two r's here is because I have the radius squared, so I need to take account of that error twice to get the error into the volume. My uncertainty in my radius is 0.008 divided by 4.005, and then I've just got that times 2, plus the uncertainty of my depth, which is 0.004 divided by 0.506. At this point it doesn't matter what the units of this are because I'm taking a fractional error. Units top and bottom are going to cancel. So if I just work that out, so this one here is 3.995 times 10 to the minus 3 plus this one is 7.905 times 10 to the minus 3. And so my total error here is 0.0119. And this is equal to the error in my volume divided by my volume. So if I have my error in my volume, it's just this value here multiplied by the volume that I determined, which was 6.37 centimetres cubed. And so I need to round this value up. This is equal to 0.08. And so my volume is equal to 6.37 with an uncertainty of 8. So I now know the volume of the coin and I'm given the density of diamond. So the density, we give density the symbol rho, and that is 3.52 with an uncertainty of 9 grams per centimetre cubed. And my volume, V, is equal to 6.37 with an uncertainty of 8 centimetre cubed. And so my mass that I have of my diamond is going to be the density times the volume. So M is equal to rho times V, which is equal to 3.52 times 6.37. Which I think is 22.4 grams. Now again, my uncertainty of my mass divided by my mass is equal to the uncertainty of my density divided by my density plus the uncertainty of my volume divided by my volume. And so here I can just put in these values. This is equal to 0.09. Remember, this 9 is an uncertainty in this last digit, so it's 0.09 divided by 3.52 plus 0.08 divided by 6.37. So this is equal to 0.038, so I'm going to take that to be 0.04. And my uncertainty of my mass is equal to 0.04 multiplied by the mass that I had, 22.4, which gives me a mass of, my mass is 22.4, and then if I calculate this, I end up with an uncertainty of 9 grams. Moles is equal to mass over my, in this case, relative atomic mass. And in this case, my mass was 22.4 grams, and the relative atomic mass of carbon is 12.011 grams per mole. And so the number of moles that I have is 1.86 moles. And again, I'm multiplying or dividing, so I'm going to use the same method of determining my errors. This time the uncertainty in the number of moles divided by the number of moles is equal to the uncertainty in the mass divided by the mass plus the uncertainty in the relative atomic mass divided by the relative atomic mass. Now the important thing to remember is it doesn't matter whether I'm multiplying or dividing, all of these terms add up in terms of my error. Now if I think about this just very, very simply, the uncertainty in my mass is equal to 0.9 divided by 22.4. And the uncertainty in my atomic number from the question, the relative atomic mass is given as 12.011 with an uncertainty of 1 in this last figure. So this is 0.001 divided by 12.001. This is tiny compared to this. I can just ignore it, essentially. So, being able to spot quick tricks like this is really, really useful. This is a tiny, tiny number compared to this one. So, if I remember from before, this was 0.04. And so, my uncertainty in my number of moles is equal to 0.04 multiplied by 1.86, which is equal to 0.07. Therefore, the number of moles is equal to 1.86 with an error of 7 in that last number. And then my unit of moles. So the final part of this question was working out how many atoms I have. So if I know the number of moles I have, So n is equal to 1.86 with an uncertainty of 7 in that final number, moles. So the number of atoms is equal to n times Avogadro's number, the number of atoms in a mole. And this is a fixed exact number. So my uncertainty here is just going to play directly into this one. This doesn't have an uncertainty, so it adds 0 to the term effectively. So this is equal to 1.86 multiplied by 6.0221 times 10 to the 23. So here my number of atoms is 1.12 times 10 to the 24 atoms. Just a small note here, all the way through I've been thinking about this in terms of 3 significant figures in, 3 significant figures out. So now the uncertainty in, I'm just going to call this uncertainty in atom divided by number of atoms is equal to my uncertainty in my moles divided by my number of moles, which I have 0.07 divided by 1.86. So 7 uncertainty in this last digit divided by this is equal to my number of atoms, my uncertainty in my number of atoms divided by my number of atoms. And so if I just multiply this value here by the number of atoms I have, so 0.07 divided by 1.86 multiplied by 1.12 times 10 to the 24. Then I find out that my uncertainty in my number of atoms is 4.21 times 10 to the 22. So don't really care about these two numbers, so 4 times 10 to the 22, which means that I've got an uncertainty of 4 in this very, very last digit here. So this becomes n is equal to 1.12 with an uncertainty of 4 times 10 to the 24. Sorry, this isn't n, of course. This is the number of atoms. So I hope that helps you along. And if you have any more questions or you want any more videos, please feel free to contact me.